Hello student, myself Nimesh Prabhakar. Welcome to Antenna and Propagation lecture series. In my previous lecture, we discussed about the monopole antenna. Now, in this lecture, we discuss about the third one type of dipole antenna, that means half wave dipole antenna. So we know that there are three types of dipole antenna. First one is the oscillating dipole, that is nothing but the Argentine dipole. Then second one is the small dipole antenna. We also discussed the monopole antenna. And now we discuss last one type of the dipole antenna is the half wave dipole antenna. So here in this lecture we discuss the part 1 of the half wave dipole antenna. So this is the figure for the half wave dipole antenna. Half wave dipole is one of the simplest antenna which has physical length of half wavelength. That means we know that the L is the length of the antenna. So here the half wave dipole. So that's why here the L is equals to lambda by 2. So the name is given the half wave. That means we know that the lambda is the wavelength, and when the L is equals to lambda by 2, so that antenna is known as the half wave dipole antenna. The lambda by 2 antenna is also known as Hertz antenna. It is one of the most commonly used antenna, and the antenna field, this antenna is mostly used in a different application. Because its radiation resistance is 73 ohm, it can be connected to 75 ohm transmission line more easily for matching purpose. So this is the reason why this antenna is more commonly used in a different application, because the radiation resistance of this antenna, that means the half wave dipole antenna, is 73 ohm. So we can easily connect this antenna with the 75 ohm transmission line. So here the matching, that means mismatch of the resistance or the impedance mismatch is very low. So that's why we use this half wave dipole antenna more in the application. Now we calculate radiation field of half wave dipole and its radiation resistance. So now we start the analysis of the half wave dipole antenna. So before we start the analysis, we take some assumptions. So what are they? So first one assumption is the lambda by 2 antenna is placed in a coordinate system such that axis of dipole coincide with the z axis and the center of the dipole is at origin. So this is the first one assumption. Now second one assumption is the current is fed at the center of the dipole using the transmission line. Third one assumption, the current on the dipole is sinusoidal such that I is equals to I0 sin k h minus z for 0 less than or equals to z less than or equals to lambda by 4. And for the second one, the I is equals to I0 sin k h plus z for minus lambda by 4 to 0. So now this is the assumption. Next one is the medium surrounding the antenna is air. So here we also take another assumption. The medium, the surrounding of this antenna is also the air. And last one, the diameter of wire is very small as compared to wavelength. So the diameter of the wire is very small. Here we take as compared to the wavelength. So we can write that D is very less than the lambda. So these are the assumptions. Now we discuss about the E and H field. So to find the electric and magnetic field, we start the procedure. So first one step to find this is first we find the magnetic vector potential A. So now we start the analysis of the half wave dipole. So first one step, we know that in the same we discussed it in the oscillating dipole. First we find the magnetic vector potential A. The field due to the dipole can be obtained if we consider it as a consisting of a chain of Hertzian dipole. The magnetic vector potential at P due to a differential length dl is equals to dz of the dipole carrying current I is dAz is equals to nu I dz 4 pi into r e raised to minus j beta r. Here this r is indicate the distance between I dz and point P. Now the magnetic vector potential, in that when we add vector magnetic potential due to all differential element present from z is equals to minus h to z is equals to h, we get total vector magnetic potential at P is Az is equals to minus h to h into dAz. So we can write the value of the dAz in this equation. So we can write Az is equals to minus h to h nu I dz 4 pi r e raised to minus j beta r. The problem in solving this integral is current is not same over total length of the antenna. So here the current is not same over the total length of the antenna. We know that the negative polarity, positive polarity. So current is changed. So the expression for current from H is equals to minus H to Z is equals to 0 is different from Z is equals to 0 to Z is equals to H. So we can write this integration in the two portions. First one is the minus H to 0 and second one portion is the 0 to H. So here we divided this integration formula in the two portions. First one is the minus H to 0 and second one is the 0 to H. So now we start this integration process. In the figure, the difference r is equals to r minus r is equals to z cos theta. R is equals to, so we can write the r is equals to r minus z cos theta. If now we consider r is greater than I, so we can write, we may substitute the r is proportional to small r in the denominator of Az expression. For the phase term, the difference between Kr and K small r is significant. So we replace r by r minus z cos theta and or we can say r. Thus we can write r equals to r minus z cos theta in numerator and r is equals to small r in the denominator term. Now equation is changed to, so we put this assumption in this equation, so we get the Az is equals to nu I0 4 pi r integration minus h to 0 sin k h plus z e raised to minus jk r minus z cos theta dz plus 0 to h sin k h minus z e raised to minus jk r minus z cos theta into dz. So now we take nu I0 e raised to minus jk upon 4 pi r as a common from this equation. So we put here the remaining term like minus h to 0 integration sin k h plus z e raised to jk z cos theta dz plus 0 to h sin k h minus z e raised to minus jk z cos theta dz. For the lambda by 2 dipole, the length of antenna is L equals to 2h is equals to lambda by 2, or so we can write the h is equals to lambda by 4. Then using the k is equals to 2 pi by lambda, the sine term in the above integral reduced as sin k h plus z is equals to sin kh plus kz. So we can write the value of the k and the value of the h. So here we write the k is equals to 2 pi by lambda and h is equals to lambda by 4. So we get sin pi by 2 plus kz, and sin pi by 2 plus kz is nothing but cos kz. Similarly, sin k h minus z we can write as cos kz. So now equation number 2 reduced to az is equals to nu I0 e raised to minus jkr 4 pi r integration minus h to 0 cos kz e raised to jk cos theta dz plus 0 to h cos kz e raised to jkz cos theta dz. So here we just write the value of the sin k h plus z and sin k h minus z. So let concentrate only first term. So here to solve this equation we take step by step procedure. So here we take the first one term. So first one term is the minus h to 0 cos kz e raised to jkz cos theta dz. Replacing z by dummy variable minus z dash. So to solve this equation, we replace the z by dummy variable z equals to minus z dash. Then we can write the dz equals to minus dz dash. Also limit is changed. Limit instead of the minus h to 0, it can change to h to 0. So the integral become minus h to 0 cos kz e raised to jkz cos theta dz. So now we substitute the assumption. So integration, the limit is changed. Integration h to 0 cos minus kz dash e raised to jkz dash cos theta minus dz dash. So we solve this. So integration we put here 0 to h cos kz dash e raised to minus jkz dash cos that dz dash. Again replacing dummy variable z dash by z. So we get minus h to 0 cos kz e raised to jkz cos theta dz 0 to h cos kz e raised to minus jkz cos theta dz. Now putting this in the equation number 4. So we can get az is equals to nu I0 e raised to minus jkr upon 4 pi r integration 0 to h cos kz e raised to jkz cos theta plus e raised to minus jkz cos theta dz. We have e raised to j phi plus e raised to minus j phi is equals to j cos phi. We know that in the trigonometric e raised to j phi plus e raised to minus j phi is nothing but the j cot phi. So now we put this in this equation. So we get az equals to nu I0 e raised to minus jkr upon 4 pi r integration 0 to h cos kz z cos kz cos theta dz. So using the identity 2 cos phi cos alpha is equals to cos alpha minus beta plus cos alpha plus beta. We know that this equation. So now we use this identity. So it becomes az equals to nu I0 e raised to minus jkr upon 4 pi r is the common. So now we use this identity 0 to h cos kz 1 plus cos theta plus cos kz 1 minus cos theta dz. So solving the integral and putting the value h is equals to lambda by 4 in this equation. So we get az equals to nu I0 e raised to minus jkr upon 4 pi r sine kz 1 plus cos theta upon k 1 plus cos theta, and the sine kz 1 minus cos theta upon k 1 minus cos theta, and the integration term from the 0 to h is equals to lambda by 4. So now we solve this equation. So we can write this equation as 1 minus cos theta sine kz 1 plus cos theta, and 1 plus cos theta sine kz 1 minus cos theta, 1 plus cos theta and 1 minus cos theta. And after putting this limit term, that means lambda by 4 to 0, so we get this term as a sine kz 1 plus cos theta is equals to sine 2 pi by lambda, lambda by 4, 1 plus cos theta. So we write the sine pi by 2 is equal to sine pi by 2 plus pi by 2 cos theta is equals to cos pi by 2 cos theta. So also we can write for the sine kz 1 minus cos theta. So sine pi by 2 minus pi by 2 cos theta is equals to cos pi by 2 cos theta. So now we put this in this equation. So we get the Az is equals to nu I0 e raised to minus jkr upon 4 pi kr 1 minus cos theta cos pi by 2 cos theta plus 1 plus cos theta cos pi by 2 cos theta upon 1 minus cos square theta. So we get, now we solve this equation. So nu I0 e raised to minus jkr upon 4 pi kr is the common, and 1 minus cos square theta is nothing but the sin square theta. And now we solve this upper term, that means in the numerator term, the cos pi by 2 cos theta, we take the common, and 1, so we get the 1 minus cos theta plus 1 plus cos theta in the upper term. So we get this 2 cos theta pi by 2 cos theta upon sin square theta. So we solve this equation further. So finally we get the Az is equals to nu I0 e raised to minus jkr upon 4 pi kr cos pi by 2 cos theta upon sin square theta. So this is the magnetic vector potential A. So in this lecture we start the analysis of the half wave dipole, and we find the magnetic potential vector Az. So here this is the half wave dipole part 1. Now in next lecture we will discuss this half wave dipole part 2. Thank you.